Have you ever, really struggled with a map? I mean, maybe one of those old nautical charts, or just looking at a world map and seeing Greenland blown up to, the size of Africa. It's this fundamental thing, right? You just can't perfectly flatten something curved, like the Earth, or heck, even just a balloon, onto one flat sheet without totally distorting it.
Exactly. And that exact problem, that frustration, is actually what pushed mathematicians way back to develop this really powerful idea, the manifold. It's kind of the secret sauce, you know? It lets us handle these complicated curved spaces, think the Earth or even space-time in physics by basically treating them as flat, but only in tiny little pieces.
Okay, so let's try and unpack that. The mission here is to get our heads around this manifold idea. The definition, it sounds a bit abstract, but it all comes back to that local flatness thing, yeah?
Yeah, absolutely. That's the core. A non-dimensional manifold, fundamentally, is just a space that if you zoom in really close at any point, it looks just like regular non-dimensional flat space, what mathematicians call math BB. Think about a sphere, right? A classic 2D example. If you're standing on it, your immediate surroundings, they look flat, don't they? Like a plane.
Right. So like a simple circle, which is 1D, if I zoomed way in on a tiny bit of it, it would just look like a straight line segment.
Precisely. And that's why a circle counts as a 1D manifold. And surfaces, like that sphere, or torus, basically a donut shape, those are your classic 2D manifolds. Locally flat everywhere.
But wait, there's a common trip-up point here, isn't there?
Yeah.
I remember reading about the figure 8 shape, like two circles touching at just one single point. That's not a manifold? Why? What breaks?
Yeah, the figure 8. It breaks that crucial local resemblance rule. Right at that single point where the circles touch, what does the space look like around you?
Like a cross, a plus sign.
Exactly. It looks like a plus. And no matter how much you zoom in on that exact point, it always looks like a cross. It never starts looking like a simple single straight line segment. And a 1D manifold has to look like a line segment locally. That crossing point just doesn't fit the definition. You can't map it smoothly onto a line there.
Got it. That makes the topology failure much clearer.
Okay.
Okay, so back to the Earth example. Since it's curved, we need an atlas, right? A whole bunch of flat maps to cover the globe. How does that work mathematically for a manifold?
Well, the mathematical atlas is basically the same idea. It's a collection of these flat maps, which we call coordinate charts. Each chart takes a little patch of the curved manifold and maps it onto flat math BRNF. But since you need multiple charts to cover the whole thing, they have to overlap. And where they overlap, that's where you need the transition maps.
Ah, the transition maps. So these are the rules that make sure if you're in an overlapping region, the coordinates from one map smoothly translate to the coordinates on the other map.
Exactly right. They have to stitch together seamlessly. If the transition maps aren't smooth or consistent, the whole structure kind of falls apart. It's all about that smooth integration.
That's smooth integration.
Yeah.
Making disparate systems work together consistently. It sounds familiar.
It's vital in math and, frankly, vital in lots of real-world problems, too.
It really is.
Yeah.
And actually, speaking of smoothly integrating complex systems, whether it's overlapping mathematical structures or maybe business processes, this deep dive is sponsored by Embersilk. So if your company needs help with, say, specialized AI training or maybe some complex software integration or even just figuring out where AI agents could best help you out, you should check out Embersilk.com. They handle all sorts of AI needs. That's Embersilk.com. Okay, back to the manifolds. The real power here, especially for physics, seems to be that you can add more structure onto this basic manifold idea, right? When did people really grasp this?
Yeah, the idea really took shape with Bernhard Riemann in the mid-1800s. He coined the German term Mannigfaltigkeit, manifoldness, focusing on defining spaces by their coordinate systems, not assuming they lived in some bigger space. And adding structure is key. If those transition maps we talked about are not just continuous but differentiable, meaning smooth enough to do calculus, then you have what's called a differentiable manifold.
Okay, differentiable. But how does that let you do calculus on a curved space? You can't just take a derivative along a curve directly, can you?
You can't, no, but the differentiable structure lets us define something called the tangent space at every point. Think of it like laying down a tiny, perfectly flat sheet of paper or a ruler for 1D that just touches the manifold at that one point. That flat tangent space becomes your temporary workspace. It is Euclidean space locally, so you can do all your calculus, find directions, velocities, derivatives right there on that flat space, and then relate it back to the curve.
Okay, that's the bridge. The tangent space is the local flat space where the calculus happens. And if you add even more structure,
Then you get into things essential for physics. Add what's called an inner product, or a metric, basically a way to measure distances and angles within those tangent spaces, and you get a Riemannian manifold. And that structure, the metric, is what lets you measure curvature. It's fundamental to Einstein's general relativity, where the curvature of space-time tells objects how to move.
Wow. So the entire universe, its shape, its curvature, is described using a concept that fundamentally just says things look flat if you zoom in close enough. That's
I-
kind of mind-bending.
It is pretty amazing. It basically says we can understand the complex curved reality by cleverly using the idea of local flatness. It's an incredibly powerful abstraction.
So next time you're grappling with a flat map of our curved Earth, just remember, that same tension, that local flatness global curve idea, is captured by the manifold. It's the tool we use to model everything from planetary motion to the very fabric of the cosmos.
It's the ultimate mathematical shortcut, really. Calculate the curve by embracing the local flatness.
Well, if you enjoyed this deep dive, please do subscribe to the show. Hey, and maybe leave us a 5-star review if you get a chance. It genuinely helps other people find us. Thanks so much for tuning in.